There's something about examining a piece of broken metal that can tell you more about a war than any battle report ever could. August 1943. A laboratory in England. A man hunched over a microscope, looking at what used to be part of Germany's most feared weapon, and he's seeing something nobody expected to find. But before we get into that, grab yourself a coffee, settle in, because what I'm about to share with you is going to change how you think about the Tiger tank forever. This isn't about glory or heroism. It's about steel, heat, and a mistake that cost Germany more tanks than the Allies ever destroyed. Stay with me until the end, and if you find this interesting, hit that like button and subscribe, because stories like this, they don't get told enough. Now, let me take you back. The piece of metal sitting on Dr. Robert Stevenson's examination table wasn't supposed to exist. Not like this, anyway. It was a transmission gear from a Tiger tank, 8 inches across, 2 inches thick, and it had failed. Not gradually, not after years of wear. It had simply shattered. Clean break, through hardened steel. Stevenson had been a metallurgist before the war, worked with Vickers Armstrong, analyzing steel for British warships. Good work, important work. But when 1939 came around, the War Office had other plans for him. They needed people who understood metal at a level most couldn't grasp, people who could look at enemy equipment and see not just what it did, but why it failed. And by August 1943, Stevenson had seen his share of German tanks. Panzer IIIs, Panzer IVs, captured, destroyed, dissected. Generally, he had to admit, they were well made. German engineering had a reputation for a reason. The transmissions worked, the steel held up, the machinery functioned. But the Tiger was different. This wasn't the first failed Tiger transmission that had crossed his desk. It was the 7th. Every single Tiger that British forces had captured and shipped back to the School of Tank Technology at Chobham Airfield arrived with transmission damage. Some of it minor, some of it catastrophic. This one was catastrophic. The entire final drive assembly had destroyed itself. Metal fragments scattered throughout the gearbox like shrapnel. The transmission had failed so violently that it locked the drive sprockets completely. The tank just stopped, became a stationary target. Eventually, the crew abandoned it, and British forces recovered it intact near Tunis in May. But here's what made Stevenson pause. Intelligence reports were showing him a pattern he couldn't ignore. Tiger tanks weren't just failing occasionally. They were failing constantly. More Tigers were being lost to mechanical breakdowns than to enemy fire. Let that sink in for a moment. Germany's answer to Soviet heavy armor, the tank that was supposed to be invincible, armed with the famous 88mm gun, protected by a 100mm frontal armor, powered by a 700-horsepower engine, couldn't make it to the battlefield. The statistics were almost absurd. Of roughly 1,300 Tigers produced by mid-1943, fewer than 700 were operational at any given time. The rest, broken down, waiting for parts, waiting for repairs, or just abandoned, because fixing them was impossible. Half of all Tigers suffered major mechanical failure before completing their first operational mission. And most of those failures were transmission-related. Stevenson stared at that broken gear and knew his job was to figure out why it failed. Not just that it failed, but what made it fail, what was happening inside the metal itself. He started with the basics, examined the fracture surface under magnification. What he saw told him immediately the fracture was brittle. No bending, no tearing, no gradual deformation, just a clean snap straight through the material. That meant this gear didn't wear out over time. One moment it was working, the next it shattered. He pulled out a Rockwell tester, pressed a diamond tip into the gear's surface, measured how deep it penetrated. The reading came back at 62 on the Rockwell C scale. He tested multiple spots. Same result, 62 to 64 HRC across the surface. Now, if you're not familiar with metallurgy, let me explain why that number mattered. Transmission gears need to be hard enough to resist wear, but not so hard that they become brittle. The sweet spot is usually around 58 to 60 HRC. Hard enough to last, soft enough to absorb shock. This gear was too hard. He cut the gear in half, tested the hardness in the core, 52 HRC, much softer than the surface. That indicated case hardening, a heat treatment process where you harden the outer layer while keeping the interior tougher. It's a standard technique for gears, but it has to be done right. The case depth on this gear was 4 millimeters. Normal case depth should be 2 to 3 millimeters at most. The surface was not only too hard, it was too deep, and that combination created brittleness. Under heavy loads, under the shock of combat maneuvering, the gear would fracture. But Stephenson needed to go deeper. He cut samples from the gear, polished them until they were mirror smooth, etched them with acid to reveal the internal structure, then examined them under a microscope at 500 times magnification. What he saw confirmed his suspicions. The microstructure showed martensite, a very hard phase of steel that forms when you cool it rapidly from high temperature. Martensite is useful in the right amounts. It provides hardness, but excessive martensite without proper tempering creates a material that's hard and fragile. And this gear had almost pure martensite in the case, very little tempered martensite. The steel had been hardened, but not adequately tempered afterward. Let me explain tempering, because this is where the whole story turns. After you harden steel by heating and quenching it, you need to reheat it to a moderate temperature. This process, called tempering, reduces brittleness. It transforms some of that hard martensite into tempered martensite, which is softer, tougher, less likely to shatter under stress. Tempering is absolutely essential for gears. It's the balance between hardness and toughness that allows them to survive the shock loads they experience in operation. This gear hadn't been tempered properly. The martensite was untempered, brittle, ready to fail. Stephenson examined 6 more failed Tiger gears over the following days. Every single one showed the same pattern: excessive surface hardness, deep case depth, untempered martensite, brittle fracture. This wasn't a fluke. This wasn't one bad batch. This was systemic. Every Tiger transmission was being built with gears that had inadequate heat treatment. They were too hard, too brittle, and they would fail under the stress of normal operation. Sharp turns, sudden stops, rapid accelerations, the kind of maneuvering you do in combat. Those maneuvers create shock loads on gears. Properly treated gears can absorb those shocks. Tiger gears couldn't. They shattered. By late August 1943, Stephenson had written his preliminary report. It was detailed, technical, and damning. He documented the excessive hardness, explained the inadequate tempering, estimated what this meant in the field. His conclusion was clear. Tiger tank transmission gears would fail under shock loads encountered during combat maneuvering. The failure would be catastrophic, sudden, with no warning. Once it started, the transmission would become inoperable. The tank would be immobilized. But here's where it gets interesting. Stephenson added a tactical recommendation. He suggested that Allied armor commanders be informed that German Tiger tank transmissions were vulnerable to mechanical failure, and that aggressive maneuvering by Allied tanks might induce Tiger transmission failure even without direct combat. Think about that for a moment. He was suggesting that you could defeat a Tiger tank not by shooting it, but by making it move. The report went to Major General Percy Hobart, a man who understood that destroying enemy tanks wasn't only about firepower. Hobart saw immediately what Stevenson's findings meant. If Tiger transmissions failed under stress, then Allied tactics should create stress, force the Tigers to maneuver, to turn sharply, to accelerate and brake hard. Each maneuver would stress the transmission, increasing the probability of failure. Hobart circulated the report in September 1943. It was classified, secret, limited distribution, but the tactical recommendations were clear. When engaging Tigers, try to force aggressive maneuvering, use flanking attacks, rapid position changes, create situations that require the Tiger to turn sharply or reverse direction. A Tiger with a failed transmission was a Tiger removed from the battle, without firing a single shot. Some field commanders were skeptical when they first read this. The idea that you could defeat a tank by making it drive seemed absurd. Tanks are designed to move. Transmissions should withstand maneuvering. But they tried it anyway. During engagements in Italy in October 1943, British tank commanders started reporting something unusual. Tigers that maneuvered aggressively would sometimes just stop. Not destroyed, not burning, just stopped. Crews would abandon them. Later examination showed transmission failure. The pattern repeated itself. Sicily, Italy, and later Normandy. Tigers were breaking down during combat at rates far exceeding normal mechanical failure rates. German after-action reports described the problem, mentioned transmissions failing during engagement. They attributed it to combat stress, poor maintenance, inadequate spare parts. They never realized the root cause was metallurgical, that the heat treatment process was fundamentally flawed, that every Tiger transmission was in essence a mechanical time bomb. Stevenson continued his analysis through 1944, examining transmissions from Tigers captured in different theaters, built in different months, produced by different factories. The pattern was always consistent: excessive hardness, inadequate tempering, brittle fracture. The problem wasn't isolated to one factory or one production run. It was endemic to Tiger production across the board. But that raised an obvious question. Why? Why would Germany build transmissions with inadequate heat treatment? Germany had excellent metallurgists, excellent facilities. The knowledge existed, the capability existed. So why were the gears wrong? Stevenson investigated German heat treatment procedures through captured documents and interviews with captured German engineers. The answer emerged slowly, and it was more complex than simple ignorance. Germany was under intense production pressure. Tigers were desperately needed on the Eastern Front. Production schedules were compressed. Every Tiger had to be completed as quickly as possible. And heat treatment? Heat treatment was a bottleneck. The proper process took time. Carburizing gears, heating them in a carbon-rich atmosphere to infuse carbon into the surface, that took hours. Then quenching in oil to harden them, then tempering to reduce brittleness. Each step required time, furnace capacity, skilled workers. And by 1943, Germany was running out of all three. Time was inadequate, furnace capacity was strained, and skilled workers were being conscripted into military service, replaced by forced laborers and minimally trained personnel. These replacement workers didn't understand metallurgy, didn't understand the importance of precise temperature control, didn't understand that tempering was essential, not optional. They followed simplified procedures: carburize, quench, ship. Tempering was skipped or abbreviated. It saved hours per gear, increased throughput, allowed more Tigers to be completed each month. The cost was reliability. The gears were hard but brittle. They would fail under stress. But those failures happened later, in the field, not in the factory, not during acceptance testing. The factory met its production quota. delivered Tigers on schedule. The transmission failures? Those were someone else's problem. This pattern repeated throughout late-war German production. Quality sacrificed for quantity. Procedures simplified. Corners cut. The equipment looked fine, performed fine under light conditions, and failed catastrophically under combat stress. Stevenson documented this in his reports, noted that the problem was systemic, not specific to one component. Germany's industrial base was collapsing. Quality control was evaporating. And his analysis proved correct. By 1944, German equipment reliability was catastrophic across all systems. Tanks, aircraft, submarines, artillery, everything was breaking down at rates that would have been unacceptable in peacetime. Germany couldn't sustain military operations, not because of lack of courage or tactical skill, because the equipment didn't work, because transmissions failed, because engines seized, because the steel was inadequate, because the metallurgy was wrong. After the war, Allied technical intelligence teams systematically examined German production facilities. The story of Tiger transmission manufacturing emerged in detail. The gears were produced by multiple subcontractors. ZF Friedrichshafen was the primary manufacturer, but also Maybach and smaller firms. Each facility used slightly different procedures, but all faced the same pressures. Produce more, produce faster, quality is secondary. Workers described the environment: 12-hour shifts, minimal breaks, constant pressure from supervisors, production quotas that had to be met regardless of circumstances. The heat treatment furnaces ran continuously, loaded with gears, heated, quenched, unloaded, immediately reloaded. No time for proper temperature verification, no time for adequate tempering cycles. The process that should have taken 16 hours was compressed to 8. The gears came out hard, but wrong. One worker, a Czech forced laborer named Josef Novak, gave testimony in post-war interviews that revealed something important. He said, "We knew the gears were not right. We could see it in how they looked after quenching. The color was wrong, but we said nothing. We were not German. Why should we care if German tanks broke down? Better that they break than kill people." The quality problems weren't purely accidental. Some workers deliberately produced substandard components, sabotage by negligence, allowing the process to drift, not reporting problems, not maintaining equipment. Small acts of resistance that accumulated into massive quality degradation. German supervisors knew something was wrong. Transmission failure rates from field units were reported, documented, impossible to ignore. But the production system couldn't respond, couldn't slow down, couldn't implement proper procedures. The pressure from above was relentless. More Tigers, more tanks, more production. Quality problems were acknowledged, then ignored. The priority was numbers. Numbers of Tigers completed. Numbers delivered to combat units. What happened after delivery wasn't the factory's concern. This institutional failure is documented in German records. Reports from the Waffenamt, the Weapons Procurement Agency, describe the situation. They mention inadequate quality control. They mention skilled worker shortages. They mention production pressure. They recommend improved procedures. The recommendations were filed, not implemented. The system couldn't change, couldn't slow down, couldn't implement the underlying problems. So the Tigers kept being built, kept being delivered, kept breaking down. By early 1945, Tiger transmission reliability was so poor that German tank units were requesting different tanks. They preferred Panthers. They preferred Panzer IVs. Anything but Tigers. The Tigers were too unreliable, broke down too often, required too much maintenance, consumed too many spare parts. The tank that was supposed to dominate the battlefield had become a liability, a maintenance nightmare, a machine that failed more often than it fought. Stevenson continued his analysis through the end of the war, examined Tigers captured in France, Belgium, Germany itself. The pattern never changed: excessive hardness, inadequate tempering, brittle fracture. Every Tiger, every transmission, every gear. The problem was never fixed, couldn't be fixed. The industrial system that created it couldn't be reformed. When Germany surrendered in May 1945, Tiger production ended. The transmission problem became a historical curiosity, a subject for post-war analysis, a lesson for future tank designers. And Stevenson's work, it influenced post-war British tank design significantly. When Britain developed new tanks in the 1940s and 1950s, transmission reliability was a priority. Heat treatment procedures were specified precisely. Tempering was mandatory. Quality control was rigorous. The lessons from Tiger failures were applied. The result were transmissions that worked, that survived combat stress, that didn't shatter under shock loads. Stevenson retired from government service in 1955, took a teaching position at Imperial College London. His students knew he'd worked on wartime projects. They didn't know specifics. Stevenson didn't discuss it. The work had been classified. And the memories? They were complicated. He'd saved Allied lives by finding German weaknesses, but those weaknesses existed because German workers were exploited, forced to work under impossible conditions, producing equipment that killed their own soldiers. The morality wasn't simple. Stevenson did his job, analyzed the metal, measured the hardness, examined the microstructure, wrote the reports. The strategic implications, those were someone else's responsibility. In 1976, a graduate student named Thomas Richardson was researching tank reliability for his dissertation. He contacted Stevenson, asked for an interview. Stevenson was 72 years old by then, retired but still lecturing occasionally. He agreed to meet. Richardson visited on a spring afternoon. They sat in Stevenson's office at Imperial College. Books on metallurgy everywhere. Old journals. Photographs of metal microstructures. Richardson asked about the Tiger transmission analysis. Stevenson described it: the excessive hardness, the inadequate tempering, the brittle fracture, the realization that Germany was building tanks that couldn't survive their own power. Richardson asked the obvious question: did you feel satisfaction knowing your work contributed to defeating the Tigers? Stevenson thought carefully before answering. Satisfaction? No. The Tigers were defeated by their own inadequate manufacturing. I just documented it. Someone else would have found the same problem eventually. Probably a German metallurgist did find it. Probably reported it. Probably was ignored. The problem wasn't lack of knowledge. It was lack of ability to implement solutions. Germany couldn't slow production, couldn't fix the heat treatment, couldn't properly temper the gears, so the problem continued. I documented that, used it to understand enemy capabilities. But satisfaction? No, just recognition of systematic failure. Richardson included Stevenson's analysis in his dissertation, published in 1978. The title was Reliability as a Weapon: Mechanical Failures in German Armor 1943 to 1945. The Tiger transmission received an entire chapter, 28 pages, detailed technical analysis, metallurgistic data, heat treatment specifications, failure statistics. The dissertation didn't attract wide attention. Academic work rarely does. But tank designers read it. Metallurgists working in armor development read it. The information became part of institutional knowledge, part of how modern tank transmissions are designed. Modern tank transmissions use gears with carefully controlled heat treatment. Case depth is specified precisely. Hardness is specified precisely. Tempering is mandatory and verified. Quality control includes metallurgical examination. Sample gears are cut apart. Microstructure is examined. Hardness is measured at surface and core. Any deviation from specification results in rejection. The entire batch is scrapped if necessary. This level of quality control exists because of lessons learned from failures, learned from tigers breaking down, learned from gears shattering, learned from Stephenson's analysis. That learning saved lives, saves lives today. Every time a tank transmission survives combat because it was heat-treated correctly, Stephenson's work echoes. Every time a gear doesn't shatter because it was tempered properly, the lesson persists. That's legacy, not fame, not recognition, just knowledge applied, just problems solved, just equipment that works because someone 80 years ago figured out why German equipment didn't work. The German perspective on Tiger transmission failures emerged slowly after the war. Former tank crews wrote memoirs, described the frustration of mechanical breakdowns, described Tigers abandoned because they couldn't move. One commander, Otto Carius, who survived the war commanding Tigers on the Eastern Front, wrote extensively about transmission problems. He described how his unit's operational readiness never exceeded 60%, how at least 4 of his 10 Tigers were always broken down, usually with transmission problems. Carius attributed this to combat stress, difficult terrain, inadequate maintenance support. Reading Stephenson's analysis decades later, he understood. The transmissions were doomed from manufacture, heat-treated incorrectly, brittle gears waiting to fail. Nothing the crews could have done would have prevented it. The tanks were mechanically unsound when delivered. Every mission was a gamble. Would the transmission survive? Would the gears hold? Carius wrote that knowing this was disturbing, knowing that he and his crews had trusted their lives to machines that were fundamentally defective, that Germany had sent them into battle in tanks that couldn't be relied upon, not because of enemy action, but because of inadequate manufacturing. The feeling of betrayal was strong, not betrayed by enemies, betrayed by their own industrial system, by the decision to produce tanks faster rather than better, by the choice to ship Tigers with inadequate transmissions because meeting production quotas mattered more than reliability. Carius and other tank commanders felt they'd been lied to, told the Tiger was invincible, found it was fragile, told German engineering was superior, found it was compromised. The psychological impact was significant, undermined confidence, created cynicism, made soldiers question everything they were told. Modern analysis of Tiger tanks confirms Stephenson's findings completely. Museums preserve Tigers, metallurgists have examined their transmissions, cut gears apart, measured hardness, examined microstructure. The results match Stephenson's 1943 analysis exactly. Excessive surface hardness, deep case, inadequate tempering, brittle microstructure. The problem was real, was systematic, was never fixed. The Tank Museum at Bobington, England has Tiger 131, the only running Tiger in the world, restored to operational condition. The museum maintains the transmission carefully, uses modern lubricants, limits operating hours, avoids heavy loads. Even so, the transmission requires constant attention, frequent inspection, careful monitoring. The museum's engineers understand they're operating a machine with inherent weaknesses. The gears are original, heat-treated incorrectly, prone to failure. The tank runs because it's operated gently. In combat conditions, with combat loads, it would fail quickly. This validates everything Stephenson discovered. The Tiger transmission was inadequate for combat use, couldn't survive combat stress, failed regularly and predictably. The tank that looked invincible was mechanically vulnerable, crippled by its own drivetrain. And this vulnerability was exploitable. Allied commanders who understood it could use tactics that stressed Tiger transmissions, forced the tanks to maneuver, created situations requiring sharp turns and rapid acceleration. Each maneuver brought the transmission closer to failure. Some Tigers were defeated without firing a shot, defeated by their own gears shattering, defeated by metallurgy. Stephenson's analysis enabled this, made commanders aware, gave them confidence to maneuver aggressively against Tigers, knowing the Tigers might break down under stress. That psychological advantage mattered, made Allied tank crews less afraid, made them more willing to engage, knowing the invincible Tiger had feet of clay, had a transmission that could fail catastrophically, had gears that could shatter. Stephenson died in 1989 at age 85. His obituary in the Times mentioned his teaching career at Imperial College, mentioned his contributions to metallurgical science. One sentence mentioned wartime service. During the war, Professor Stephenson contributed to military equipment analysis. No details, no mention of Tigers, no mention of transmission gears, no mention of discovering that Germany's most feared tank had a fatal mechanical flaw. That information was in archives, in declassified reports, in dissertations that few people read. Stephenson's family donated his papers to the Imperial War Museum. The reports sit in archives now, available to researchers, rarely requested. The story of Tiger transmission failures is known to specialists, unknown to general audiences. The popular narrative about Tigers focuses on their firepower, their armor, their combat effectiveness when they worked. It doesn't emphasize that they frequently didn't work, that mechanical reliability was abysmal, that transmissions failed constantly, that the root cause was inadequate heat treatment, that the cause was documented thoroughly by a British metallurgist in 1943. That documentation influenced tactics, influenced outcomes, influenced how the war was fought. You know, there's something profound about understanding that wars aren't just won with courage and firepower. They're won by people who understand that a gear with 62 HRC surface hardness and inadequate tempering will fail under shock load. By people who know that forcing a Tiger to turn sharply might shatter its transmission. By people who exploit knowledge, who exploit weakness, who exploit metallurgy. Stephenson did that, analyzed the steel, measured the hardness, examined the microstructure, wrote the reports, changed how the war was fought, never sought credit, just did the work. And that work, it persists. In every tank designed since, in every transmission engineered to survive combat loads, in every quality control procedure that requires metallographic examination, in every specification that mandates proper tempering. The mistakes aren't repeated. Modern tanks work because engineers learned from German failures, learned from Tigers breaking down, learned from gears shattering. That's what matters. That's the real story. Not the myth of the invincible Tiger, but the reality of inadequate heat treatment, of production pressure overwhelming quality control, of skilled workers replaced by forced labor, of tempering skipped to save time, of gears that looked perfect and shattered under stress, of a British metallurgist who figured out why and helped defeat them. So there you have it. If this kind of deep dive history is your thing, there's plenty more where this came from. Matter of fact, I've got another video. You can check that out next by clicking up here, and I'll catch you over there.